Just subsequently, it was taken up seriously, and the algorithms how to do quantum computation was there and was developed in early 80s. There were two beautiful papers. One is about this basic steps, namely Hadamard and Contonot, that you need a 2 by 2 matrix and a 4 by 4 matrix to carry out any quantum computation. And the mathematics is the mathematics of vector spaces, unlike mod through addition of classical computation. Just to remind you, for the young people, that in all our classical computation, we have this very simple rule. 0 plus 1 is 1, 1 plus 0 is 1, 0 plus 0 is of course 0, 1 plus 1 is 2, which is actually 0. So this mod 2 mathematics is the mathematics behind all the classical computation. What are the 0 and 1? They are called C-bit. And practically, they are actually no voltage. You have small silicon ions, no voltage is 0, some amount of voltage depending on the system at hand is 1. So and you built up the whole thing starting from there. And the 70s was the time when people found out that they cannot pack any more circuits. This so-called Moore's law, every 18 months you can double the amount of things which you can pack in a given size. That was breaking down primarily because of heat. That led to very fundamental understanding of generation of heat, that it arises because of non-reversible processes. And Professor Singh would remember in early 60s there were papers by Landauer, which condensed matter people use extensively. He pointed out that information is actually loss of information is heat. To be very precise, 1 C-bit information cost is half kT. You see the precise nature of 61 paper. 1 C-bit information is half kT. So this and this law is valid. People have checked experimentally. So then, beginning of the middle of 70s, people pointed out that this heating is because of this thing. If you can do avoid these kind of irreversible processes, then heating can be avoided. Now, as usual, there was a great creative person, an Italian person called Toffoli. He came up with a circuit which has been used in many of these things, that you can actually have a circuit which avoids this. It was used without understanding how it works. Later on, people found out that is because it's a quantum mechanical operation, unitary operation. So unitary matrices. It was appreciated that all the operations carried out by unitary matrices are reversible, hence won't cause any heat. So 80 to 90 laws, like for example, you cannot Xerox a quantum file, no cloning theorem. Then Feynman's idea about quantum computation. Then the idea that two matrices are enough to carry out quantum computation of any complex object, Hadamard and Prof. That was in 80 to 90. Then came the 90s, and the heroes of those two 90s are the Peter Sword and David and our Locke Grover. Grover was the product of IIT Roorkee, Meerut. He is from Meerut, and very simple. He is not a quantum physicist. He understood only mathematics of polymatrices. And if some of you please spend your time, and we can really find out that a lot of things you can learn from this Grover's search algorithm. Essentially, you are given a state psi, you are looking for another state which is a part of it, and how do you arrive from this arbitrary state psi to the state which you are looking for? By carrying out two operations. And I think operations are so simple that you will be amazed to see when you carry out those operations. It involves an operator, identity, minus 2 times outer product of psi, identity minus 2 times outer product of the state we are looking for. You will find out that how through this you have to do multiple times, and very quickly you will come up with the state we are looking for with high probability, and it is optimal. And it's such a beautiful, simple algorithm with the two inputs what you are looking for, nothing more. And these operations consecutive to two operations. Many people believe that nature must be taking advantage of it. So particularly in processes like photosynthesis and and other processes which people believe quantum coherence plays a role. This may be having the role in it. Now, why is that? Because two principles are used in quantum computation. One is superposition, one is entanglement. Now, this Grover search does not depend on entanglement. It only depends on superposition. Peter Sword 1994 who showed that through quantum Fourier transform, taking advantage of entanglement, you can actually solve this difficult problem of factorization. Why it is difficult? Multiplication is easy. 7 times 3 is equal to 21. But if you want to factorize 21 is equal to 7 times 3, it may be difficult, particularly if that number is big. You will be amazed to see that NMR quantum computers in the beginning, front page of the nature was 21 is equal to 7 times 3. You may wonder why is 21 is equal to 7 times 3 such a big deal? Because NMR people showed Peter source algorithm is correct. So those two are stood test of time. One more which was developed by Seth Lloyd and company in 2009, solving linear equations that also have stood test of time. Since then, all the algorithms where people have claimed there is a quantum advantage have been questioned. And to the best of my knowledge, I don't see any algorithm which has concurrently shown that quantum has an advantage. So in fact, Google has announced $5 million a few weeks back if you can actually show quantum advantage of some algorithms. So young people, you have a great challenge. Very nice. So what are these qubit? Qubit are actually column vectors. Thanks to Dirac, we have this brand K notation. Anybody who knows spin matrices, Pauli matrices will be able to handle it. 0 is the state 1, 0, column vector. 1 is the state 0, 1. They are orthogonal. They are somewhat like unit vectors I and j. We are familiar in representing a vector on the plane through unit vectors I and j. I square is equal to j square is equal to 1. I dot j is equal to 0. And they are the building blocks, namely the unit vectors. 0 and 1 are the unit vectors. They have all the exactly same properties like I and j. Superposition of that is allowed, and we know superposition gives rise to coherence and therefore interference patterns. Same thing happens here. What are these 0 and 1? Any two-level system. For example, in case of atoms, 2 levels. Atom quantum dot, yesterday I was mentioning 2 levels. Anywhere you identify 2 levels which are orthogonal, can act as 0 and 1. So for example, I will give you some examples later on. So where do physically people realize these qubits? Superconducting qubit is known to be part of now IBM quantum computers. And if you look at this circuit, they pretty much look like our electronic circuit, LCR circuit. But the building blocks are the superconducting qubits. So superconductors are macroscopic states of matter. So therefore, building things from there is intrinsically quantum and macroscopic. So superconducting qubits naturally, but the only problem is that you have to cool them to very low temperature. Hopefully that may be avoided because there was a paper published on TIFR only a couple of months back, I think last month probably, where they have shown this high TC superconductor possible to design a diode. Very nature physics paper, if I remember correctly, only last month. If that is true, liquid nitrogen can be used. The quantum dot, for example, Samsung uses now quantum dot. Many people are getting into quantum dots. So quantum dot, for example, there are some very elementary beautiful articles, including, if I believe properly, then Professor Vijay Singh also has a couple of articles that how the quantum dots are essentially like macroscopic atoms. And 2 levels you can easily identify. And they have been studied for quite some time, so they are robust. So now they are being used as building blocks for quantum, so 0 and 1. If they can talk to each other through photons. Trapped ion, for example. Now physically quantum computers very robust. 20 qubits out there in the market. So there's a company called IonQ, which actually sells these machines, very robust. Why? Because ions repel each other. So it is not prone to noise that much. So these are out there in the market. And and what we hear from grapevine that 50 qubit ion trapped ion will be out in the market very soon. But photonic qubits are primarily for communication. For example, every country now has a program. As I mentioned yesterday, PRL, then IIT, Delhi, DRDO, ISRO, UBC, RRI. There are many programs where photonic qubits are being used for communication, primarily for quantum key distribution. Quantum key distribution, for example, is very elementary. Only thing is the equipment what you need to do it is a bit sophisticated. You need one single photon emitters, entangled photons emitters, for which you need these nonlinear crystals, detector of single photons. Those are the kind of things what you require. maybe, if you find time, do visit some of these labs. And in IIT Kanpur, in, Delhi, IIT Delhi, IIT Bombay, those kind of places, it's nice for you to see how really they are doing it. Very good. So photons and qubits. Light is intrinsically, quantum, as we know. Max Planck pointed out, Einstein pointed out, they behave like particles. So those are being used. But only thing is that photons don't talk to each other. They move always with speed of light, and their interaction is not very strong. So physically, how do you manipulate it so that the interaction is strong, you can control it? It's a challenge. In that regard, for example, some of you who have energy and not very difficult to read, read, for example, something called circuit QED. Circuit QED. It was worked out very simple mathematics in Yale, two-level systems, based on two-level systems, quantum electrodynamics of circuits literally. So that is the mathematics behind superconducting qubits, and it's used in a computer, quantum computer. Simple mathematics. What it shows is that when many atoms are present, this coupling between them and photons can be enlarged. There is nonlinearity which comes in, the factor of n comes in there. So this interaction can be straightened. Similarly, you might have heard about Rydberg atoms. These are atoms where the electron is far away from the nucleus, large n. So they're almost like classical objects. It's like orbit, electron is moving in the orbit. They have a huge, big dipole moment. So they have been studied for quite some time because of that fascinating, almost classical-like property. So they are now being used for neutral atom qubit. And believe me or not, people are claiming that neutral atom qubit very quickly within this year will be released in the market. There are Alan Aspect is one of the persons in the company. This person Lukin from Harvard is there, and 127 or 200 qubit neutral atom based quantum computer will be out in the market very soon and most reliable. Very good. Defect based qubits, many of the Indian people are working on it. Nitrogen defect in diamond, one classic example. Apparently very simple 0 and 1 system. Topological qubits, there are physical realizations, but this is the thing of the future. For example, Hall effect and quantum Hall effect. As you know, roughly speaking, topology does not get affected by noise. So noise resistance is one of the key factors of topological qubits. So there was some claim that Microsoft had betted on this Majorana fermions. There are some experimental setbacks because of which it's not yet into any of the circuits, but hopefully it will soon come. Because now there are these pretty symmetric materials, chiral materials, all the Cornish matter people are realizing the dream objects, good dimension, graphene, which are actually pretty much like quantum materials. So quantum materials are a matter of study. If you see, National Quantum Mission of Government of India has one vertical, quantum materials. So just to remind you that National Quantum Mission has four verticals: as quantum material, then quantum sensors, quantum communication, and quantum computing. And for example, there are many groups who have applied. April 6th for the deadline. Hopefully, some of you young people should get involved in it. I know IIT Patna has taken lead. Now, NMR quantum computer has been there from early on. In India, for example, Prof. Anil Kumar has done remarkable experiments using it. His students are now all over India. IISER Mohali, IISER Kolkata, IISER Pune, and TIFR, and where not. All of them are pioneering, NMR, use of NMR in quantum computation. Many things have been demonstrated through NMR quantum computer, including factorization. Okay. So superposition is the basic thing which is being used. So you see alpha 0 plus beta 1, like any arbitrary vector can be decomposed into, two unit vectors 0 and 1. Alpha and beta are complex, unlike our real vectors, but the probability is conserved. Psi mod square is equal to 1. So you can see, only thing, please remember that a psi and a overall phase, exponential I theta times psi, you cannot distinguish them because the magnitude does not get affected. If you take mod square, the phase goes away. Therefore, if you look at, there are 4 parameters. Out of that, one parameter is worthless because the phase degree of freedom is gone. And then the condition alpha mod square plus beta square is equal to 1. So therefore, there are only 2 degrees of freedom, one angle, one phase. And it was Feynman who pointed out that one angle and one phase is enough to put a lot of information. So for the curious mind, I can only point out, you can actually put in a lot of information, but how to read that thing? The moment you measure, the state will collapse. If you take the state psi, which is unknown state, then you try to measure and what state it is in. Now, there are very simple questions which will come in. Whenever you measure, they will ask, now which basis you are using? For example, in a vector, when you expand, is it spherical polar coordinate? Is it Cartesian coordinate? Which coordinate you are expanding? That's the first question. Here it is 0 and 1, or it could be, for example, something called Hadamard basis plus minus. So first you have to tell which basis, like which basis you are expanding the vectors. Measurement outcome will depend on the basis. For example, if you measure the 0, 1 basis, the way I have written here, the answer will be simply 0 or 1, completely arbitrary, no alpha beta trace. A single measurement will produce only 0 or 1, nothing more. So alpha beta information is gone. Then how do you get it alpha beta? We will know only on the quantum mechanics is probabilistic in nature. If you do large number of measurements, you will find out 0 occurs with the probability of alpha mod square. 1 occurs with the probability of beta mod square. So the statistical nature of quantum mechanics has been understood. If you remember, Born, Jordan, and Dirac, many people contributed. So this led to Nobel Prizes. So this is actually the arbitrariness, intrinsic arbitrariness of a quantum state. That the moment you measure, it will depend on the state. If you measure 0, 1 basis, outcome will be 0 or 1. And alpha beta information is gone. A single measurement will give you only 0 or 1. And amazingly, if you measure in the plus minus basis, output will be plus or minus. Then we wonder what is going on. Whichever basis you measure, outcome will be that basis. Only thing is, suppose the state is given to you as 0. And if you measure in the 0, 1 basis, nothing will happen. 0 will be 0. So if the state you are measuring and state that is given to you, if they are same in the base basis, for example 0 or 1, which is the eigenstate, state is not going to change. Otherwise, state is going to change. For example, consider this example. The state given to you is 0. You are measuring the 0, 1 basis. You find 0 will remain 0, nothing will happen. But if you measure in the plus minus basis, which is basically superposition of 0 plus 1 by root 2 or 0 minus 1 by root 2, that is equally legitimate basis. This is like a polarization basis. What you will find, state will collapse, plus or minus. Now completely arbitrary. So here you see completely determined state 0 in the 0 by 1 basis collapses to completely arbitrary plus minus basis with equal probability. So this is the root of random number generation. Very simple rule. If you go to IBM, for example, you can get access to the IBM quantum computer in 15 minutes. You can generate your own random number, 0, 1, 1, 1, 0, 0 kind of thing. So this very simple thing is the led to technology, quantum random number generator. This very simple thing that measurement affects the state has led to QKD, quantum key distributions by Bennett and Prasanta. 1984, when they were in Bangalore, they had this talk in IAC that measurement affects the state. And over glass of beer, they discovered this quantum field distribution protocol called BB84, Bennett Brassard 84. Very simple. And many people are now implementing these things. At the laboratory level, you can actually do it. All it needs is that you create single photons. Both Alice and Bobs will agree on what basis they are going to measure. And depending on the information sent, 0, 1, 1, 1, 0, 0 can be interpreted as information, what you want to send. But in between, imagine Eve is there, like yesterday I was telling. If Eve tries to measure, she does not know which state has been created, things will collapse. And Bob would know that things have collapsed because Bob knows what he is expecting based on very simple things like this. So far, what I have told you, just please go and read BB84. I mean, very good written up materials are available in the net. You find out you don't need anything more. BB84 algorithm you will understand. Okay. Very nice. Good. So now superposition is the thing which we have understood. The applications of superposition I pointed out through quantum random number generation, quantum key distribution, BB84 in particular. Those are the two things which are out there in the market. And one more thing I pointed out to you. Measurements leads to collapse of the state. Therefore, even if you store the information in alpha and beta, retrieving them is very careful kind of processing, not very easy. With a simple measurement like what I said, which is called von Neumann projective measurement, will lead the state to collapse. So many smart people have put their head into it. One idea I'll point out to you, something called weak measurement. You can check Aronov, this guy, Bohm Aronov effect. And he's now, I think, 94, 95, even now, coming up with beautiful ideas. He's the person who gave the idea of weak measurement. Namely, you can extract information without completely collapsing the state. Weak measurement. People are actually using it. Very nice novel concept called weak measurement. Please read it. And if you read it, you will find out that this thing actually people are implementing it. And you can extract partial information without destroying it. In this context, there was something which I became aware while working on it, which is called Holevos bound. Holevo, Holevo. I never knew about it. Some discovery of, let's say, only 70s, that how much of information you can extract. You can apparently extract only one bit of information, Holevos bound. So that you have to keep in mind. So there is no cloning theorem, Holevos bound, information speed cannot be faster than light. Those are the kind of constraints, please remember. Okay. And collapse of the state after measurement. All right. So now, okay, why is it not moving? I should go now. I should, yeah. So the kind of experiments, next comes entanglement. So superposition is single qubit property. Even now also, believe it or not, you can play around with superposition, think about different bases. One simple basis, please read something called maximally unbiased basis, MUB. People are actually using it. In fact, Julian Swingert in 65 wrote a very beautiful paper, single author paper in Physical Review, that when you want to extract information, what kind of measurements you should do. I was surprised to see by that time he had a Nobel Prize. And he dealt with this maximally unbiased basis, 65 Physical Review, single author paper. That has played a big role in this quantum computation domain, led to maximally unbiased basis. Different kind of basis to extract information. Still people are playing around with single qubit. And one thing I did not mention to you, something called mixed state. What are these pure state mixed state? Polarization of light, you must have seen. When you represent unpolarized light, partially polarized light, how do you do it? You have a solid ball. Surface of that is a Poincare sphere, which represents polarization of light. Each point, North Pole, South Pole, are like your, polarization of, this X and Y polarization, linear combination, then elliptic object on this, hemisphere someplace. So every point on a sphere represents a state of polarization. Poincare knew it. In NMR, for example, people have been using it left and right. But when you deal with partially polarized light, how do you discover it? Optics people also knew it. They knew it and they wrote Jones matrix, Muller matrix. What it points out to you that instead of a vector, you need to introduce matrices. To be precise, identity, sigma x and sigma y, sigma z. So if you read Hecht or Ajay Ghatak's book, you will find out that maximally unpolarized light, polarized light, fully polarized, they get all represented through the solid ball. Origin of the solid ball, which is basically a 2 by 2 matrix of value half identity, basically identity with a normalization factor half. The trace of rows will be equal to 1. That is unpolarized light. In between the origin and the surface are partially polarized light. Surface is fully polarized light. This is the mathematics which you require. This is just the mixed state in quantum computation. And mixed state called, is actually partially polarized light. So if you read Hecht, whatever you have understood there, same thing you can apply here. How to deal with identity, sigma x, sigma y, sigma z. They represent coherence. Same thing applies here also. Fully coherent or partially exactly polarized light. So please read Hecht. Now coherence part, superposition part, we are through. Single qubit. Now we go to 2 qubit. These are like, 2 electrons in case of hydrogen molecule, 2 electrons for helium. They are in a state called singlet state, ground state. They could be triplet if you supply energy, you'll be excited, triplet state. So the state which I am pointing out to you is like this. X means up, spin up, and Y means down. You can actually create. Nature, primarily we have up, down, plus, minus, down, up by root 2. singlet and triplet. But these kind of states you can actually create. They are up and plus down domain. You can also have a singlet or triplet also. So if you have this kind of thing, you do the correlations measurements. Namely, what you do is that you find out that when you do a measurement, if one is Alice, one is Bob. You see, Alice is up means Bob is up. Alice is down means Bob is down. Yesterday I was telling you about, for example, Washington, Delhi. These states, this state would extend in space from Delhi to Washington. Okay. So now, if that is true, what you find that if you measure in Delhi, Alice finds its value x, that means up. Bob will be instantaneously up in Washington. If Alice finds down, Bob will be instantaneously down. So this long range correlation, which is especially far away from each other, non-local, bothered Einstein, and it's the whole crux of Fourier paradox. And leading Einstein and our colleagues to point out that something wrong with quantum mechanics is not complete, non-locality. But these experiments, only 80s, showed that quantum mechanics is non-local. But you cannot exceed speed of light. Information goes at the speed of light maximum. And yet it is complete. So how do they show that? Very simple. For example, you can create this kind of source from which two photons will come out. Or you can create two, for example, if you take a pi naught measure decay into two photons. If when you're in Bombay, pi naught measures will produce profusely, they decay to two photons. Then the singlet state, up and down and up, exactly this kind of state, except up, down, and down, up. But very good. So what you measure in Delhi, for example, Bombay you create. In Delhi, you measure, and then far away, for example, in Egypt, you are measuring. What you'll find out, if Alice finds 1, Bob will exactly find 1. If Alice finds -1, Bob will exactly find -1. And how do you check that? Here are these coincidence detectors. You click only when -1 or 1 and 1. Okay, and this 1 -1 are like these spin projections. Okay, x, y, and z. You can take any basis as you want. For example, here I am taking this basis where it is 0 and 1. So along this axis, you could take plus minus basis here. You could take another basis along the direction. Up to depends on you. So these kind of experiments were done, and it showed that indeed this correlation exists and can exist, and it is non-local. So that led to, and to be precise, what people found out that yesterday, remember I was telling you that in this entangled state, if you compute certain combination of expectation values of polymatrices, essentially 4 terms, which for the classical case was giving me a value of 2. Remember I was telling you about this referee or this umpire doing this tossing of coins for deciding which going to bat or which going to bowl. So the combinations head, tail, head, tail. So it was Bull in 1887, I think, pointed out a suitable combination of this head, tail, 3 positive and 1 negative. It really can show that 2 or -2 is the bound for these kind of values. Same thing you replace by operators, which Bell took it from Bull to Bell in 64, and he pointed out to be 2. So between 2 to √2 lies quantum mechanics. And the experiments really showed that these 2 √2. Of course, they are very clever experiments. A lot of understanding have to be done. And that's what they did. Okay. So now, yeah. So entanglement and superposition, they are the 2 principles which are primarily being utilized. There are other things, for example. Now, what do you do? How do you create superposition and entanglement? Superposition is easy thing, Hadamard. Operation you do. Essentially, polarization optics, what we have learned, combination of polarizer and analyzer creates superposition. Same thing you do here. Entanglement creation takes place by control knot. Now, these are the 2 things. One is 2x2 matrix, one is a 4x4 matrix. That's enough. Now, entangled photons are being produced left and right. Okay, and they are being used for quantum algorithms. One of them is, for example, right now people are using for imaging. Even Jallinger have used it for imaging. Why imaging? The 2 photons are like one is up, the other is down, or one is down, the other is down. So if 2 photons are created, one is going to Washington, one is going to Delhi, the state of the photon in Delhi will tell you the state of the photon in Washington. So therefore, suppose if you want to study material property, if you want to study reactor, where you don't want to go physically, you do something called ghost imaging. You send entangled photons, one goes this way to a detector, other goes inside the detector. The state of that photon inside the nuclear reactor will be reflected by the state of the photon which you detect. See, very nice thing to do because these two are tied to each other. That is actually being used for studying material property and for even, for example, I saw a beautiful paper, Alpha from City College, was used for imaging of the brain and trying to detect cancer. You can see it's actually experimental paper. Very nice. So, who are the companies involved? These are the companies. Many of them are, now more people are coming in. As I told you, IonQ has now 20 qubit one. Microsoft has, IBM, D-Web, Rigetti, all these people are there. In fact, Rigetti has a very nice newsletter. You will see. And Government of India in MeitY is giving us access to AWS, is Amazon Web Service. So government is paying and we are actually using it. You can actually use real quantum computer through this. While you are to collaborate, then you can get access to both IBM, D-Web, Google computers sitting from here. IBM as such gives you access to noisy quantum computer. You still can do meaningful things. If you check out my early papers in my Google Scholar account, you will find out quite a few things you can do. For example, quantum check and many other small algorithms you can actually implement. Now, in fact, the challenge lies in showing what kind of useful things you can do using a noisy quantum computer. You may ask what kind of things I can do in a noisy quantum computer, but let me just tell you, give you a hint that random numbers are required for doing Monte Carlo simulation. Noisy things are intrinsically random. So therefore, can't you think that in case of Monte Carlo simulation, these things could be useful? In fact, we have recently checked a very small things. This guy Pandey, who is right now from in Jharkhand, he actually showed that through Monte Carlo simulation, when you are finding the area of a circle, most noisy quantum computer gives the area very fast using Monte Carlo simulation. You see, noisy things can be used. So error correction and error mitigation. How do you define circuits where error will be minimized? For example, people have talked about time reversed circuits so that energy, things can be cancelled. There is something called logical qubit. Use 3 qubit instead of 1 qubit. For example, 0 represent as 000 plus 111 or just 000. Use majority voting. If there is one mistake, 0 becomes 1. Something called bit flip. You correct it by using majority vote. If you have a state 000 plus 111, if phase flip occurs, plus becomes minus, parity operation can be done to check it. So you can check it out. Really right now, this error correction, smart ideas in implementing, this error avoiding rules like logical qubit and error mitigation. If there is error, what can you do still so that you get meaningful result? So these are the enormously promising research areas which are currently under investigation. And this era is called NISQ era, noisy intermediate scale quantum computing. NISQ era. And D-Wave is the one which actually is a very interesting thing. Yesterday I showed you the picture of Urmila Mahadev. So this whole thing arose in the context of D-Wave's quantum computer. People claim it is not a quantum computer, it's classical. Basically, it depends on a adiabatic process and is classical. So in fact, we showed, and there have been good works from University of California, Berkeley, Bhajirani and the students, she was one of them, that you can actually ask simple questions and looking at the statistics of experiment, you can actually see that indeed it's a quantum computer or not. This is the standard rule. Measurement statistics, just like Bell showed. Quantum is 2 to 2 root 2. They are basically measurement statistics of suitable operators. So measurement statistics is the most reliable way of checking quantumness. For example, quantum games you can play using these kind of things. You can actually device independent algorithms can be designed as long as you are in the quantum domain. Because in the quantum domain, if Alice tries to see you, something will happen. So please remember that. Okay, I think I am moving it slowly. So now, why is it not moving? Okay, so just to show you, a quantum computer is a very big machine right now, and and quantum gates I have already mentioned to you, 2x2 and 4x4 matrices. Here is the example, 2x2 Hadamard gate creates superposition. On 0 it creates 0 plus 1 and matrices 1 1 1 minus 1, very simple, 2x2. Polymatrices are the ones which are being used extensively. Control knot is the other one. So you see the truth table is that here B is controlling A, B is controlling A. So if B is 1, A will change. You see 1, 1, 1, 0. B is 1, 1, 1 becomes 1, 0. As simple as that. 4 by 4 matrix of identity, identity 0, 1, 1, 0. Only these two matrices you need to do anything. Control knot creates entanglement, Hadamard creates location. Alright. So this is the one topology designed. Now people have shown it is actually a control knot. Only where, for example, this C who is controlling, two parties are controlling the other one. Okay. So this is the one which was only unused. Alright. So now there are basically two methods. One is annular like duet and the other is circuit based. Okay, these are basically analogs. IBM and others that gate based. They're basically depending on Ising model. All right. Bell measurement, I pointed out to you that this 2 root 2 is the point. And how to create Bell state? You can actually play around in IBM. Take Hadamard, and here when you go to IBM, they will allow you to drag and draw these kind of circuits. You can actually create Bell states. You can measure them, properties of Bell state. So now there is a general state called 0, 0 plus 1, 1 by root 2 called Greenberger-Horn-Zeilinger state, which is actually very useful. Now, you believe it or not, this state property is still not very well appreciated. Two particles of which we understand. Beyond that, three particles, particularly mixed state, is more or less unknown domain. So there are some beautiful identities called triangle inequalities. If you see, Everly's has physically related paper in 2021, still trying to study these kind of states. So three particle and multi-particle in general is an open area of research. All right. So now, all right. So what are the tasks you can do? You can teleport. In fact, it's a very beautiful way. Only this, people who like IBM and technical people, when they come, they show that what all you can do using entanglement. People have actually shown experimentally. Now there are circuits which are like this. You see diagrams, Hadamard, control knot, measurement. These are the kind of things. Now this is kind of things you will see. This is one of my work which was checked experimentally by Prof. Kumar, where actually without destroying a circuit, you can find out what the condition of the circuit. Basically, Bell states you can find out if Bell state is present or not without destroying it. Simply using Hadamard, control knot and reading it outside through ancilla gate. This is a thing which I fondly remember and it has been experimentally seen. So no cloning theorem, as I showed you, is one of the theorems which you have to keep in mind. Now this is the first paper of Einstein, EPR paper, which really led to this thing. This is Bell's paper for statistical purpose. This is one of the very beautiful works of three-particle state. We showed there is something more in three particles than in two particles. Now there are lots of recent experiments, and people have now tried to, sort of entangle qubits with macroscopic object. Here you see tardigrade. This paper has already come out. So I think I'll stop here because I have taken enough time. So I'll thank you and thanks for listening. You can always send me an email. I'm accessible. Thank you.
Thank you, sir. So now I request for any query from the participants.
Yeah. Okay. Yeah.
Sir, there is one question on YouTube. What are the limits of entanglement in terms of distance and complexity?
What is the?
What are the limits of entanglement in terms of distance and complexity?
See, entanglement between two qubits is measured, through entropy-like concept. You can actually map it to entropy. And for example, you can show that for Bell state, it is 1, which is called 1 E bit of entanglement, and then 0 for separable state. Okay, so there is a method due to von Neumann. It's actually somewhat like entropy. Now, in fact, if some of people are curious, thanks to the student who came from Humeva Center, Vinith Bhaskara, we have shown that is exactly the area between post measurement vectors. You can actually show that this entropy is an area. Besides, you don't need any other concept. And it is true for higher dimensional states like 4 particle, 3 particle. This has been done with this fellow Vinith Bhaskara and Avinash and others, very recent works. So it is actually an area.
So, thank you so much.
Thank you. Yeah.
I think our President, P.K. Ahluwalia sir, is there. Sir, do you wish to share a few words?
Namaste to everybody, and I'm very happy to be with you in this lecture. Namaste, Professor Panigrahi.
Namaste, how are you?
Yes, I'm fine. We had met in Chandigarh
Yes,
in
yes.
the National Student Symposium.
Yes.
It was very nice to once again find you in programs of IAPT. And I thank you on behalf of IAPT that you have given a wonderful set of 2 lectures today and yesterday. That's great. In fact, actually, there are very good 2 programs going on nicely at the moment in IAPT. One is in RC Punjab, and other is in RC Bihar. And fortunately, all these are recorded. So these are the resources which have been generated through these 2 programs, which will be available on the quantum world and the quantum computing. Sir, there is another program which is coming up from 22nd of April, which is dedicatedly for quantum computing. And that will be for school teachers and students. So we have taken some steps to really go down to the lowest level and build up the kind of encouragement which is needed for taking up this kind of quantum technologies and creating workforce for quantum technologies at the level of IAPT. And we look forward to your help also in this particular direction. I think that will be great. And I know that the way you have given today's lecture, I was there through it almost for whole of it. I enjoyed in Chandigarh also, and today also it was a good lecture for me. Also, I know that there is another lecture listed for this today by Dr. Shraddha Singh, I believe. So, Dr. Shraddha, namaskar. And once again, on behalf of IAPT, I welcome you here. It is a wonderful program which has happened. I'm very happy about it. And now, all the speakers who participated, they are our benefactors, I would say, IAPT's benefactors. So that is also good that we are having lots of such things happening. So Vijay Singh is always there to guide us, and Professor Pandey and our president of the RC Bihar, Amrendraji, they have taken very good step to really activate RC Bihar and come up with a very nice program. Congratulations. Thank you very much.
So with this, thank you so much, Professor Prasanta Panigrahi sir. And I suppose Shraddha Singh is here. So, Ma'am Shraddha Singh.
Namaskar, sir.
So, are you ready?
Yes. Yes.
So, I now request Ms. Shraddha to please start the session.
Hello, everyone. So today we'll continue the lecture that I started yesterday. And I think, can you see my screen? Yes.
Yeah.
I think it would be important to go through some notations related to qubits from the bottom up. All right. First, let's discuss what qubits are and what their representation is. So I told you yesterday that classical bits that are used in your computation are represented are either 0 or 1. These are binary digits. For quantum, you can think of the 0 and 1 get notation. So this notation was invented by Dirac. This get notation for 0 and 1 qubits represents a column vector 1, 0 for the 0 qubit, and for the 1 qubit state, it's 0, 1. So these are the column vectors that represent the quantum bits. So basically, a quantum bit can be any such state, alpha 0 plus beta 1, a superposition of 0 and 1, which basically is a column vector alpha and beta. So this is a difference between classical and quantum. This is the main difference between the classical and quantum picture. In classical, you can only have two values, 0 and 1. In quantum, you can have a column vector which has mod alpha square probability of being in the 0 state and mod beta square probability of being in the 1 state. This is a quantum superposition property that the quantum computers use. Okay. The term qubit was actually invented by Benjamin Schumacher. And this is when we started calling these qubits, Q-U-B-I-T-S. Okay, why do we want these qubits? So quantum bits are actually pretty interesting because in classical, if you have n physical systems, you can have n bits of storage units. In quantum, if you have n qubits, which is also n physical systems, you can have 2 to the n bits of storage, in the sense that at the same time, n qubits can, because of quantum superposition, represent memory equivalent to 2 to the n bits. And that's exactly the advantage that comes from quantum in everything. For example, your computation and your Hamiltonian simulation, other things we'll talk about. But for example, when n is equal to 1, you can store and extract information equivalent to 2 bits. Now, let's discuss what are the degrees of freedom or what are the restrictions on this alpha beta, the column vector that I'd shown you, which represents one quantum state. So the first and the very first requirement is the state should be normalized. That is, mod alpha square plus mod beta square should be 1. Why so? Because mod alpha square and mod beta square are probabilities. Mod alpha square is the probability of being in the 0 state, as I showed here. And mod beta square is the probability of being in the 1 state. So since these are probabilities and these are the only two states a single qubit can be in, that means these probabilities should sum up to 1. So that's the normalization requirement. That means once you've chosen your mod beta square, you've chosen your mod alpha square also. So that's 1 degree of freedom that you're given. Then your mod alpha square, of course, because it's a sum equivalent to 1, can only be any value between 0 to 1, because again, it's a probability. If it's 0, that means you are not in the 0 state, you're only in the 1 state. If it's 1, then you're in the 1 state and not in the 0 state. If it's something between 0 and 1, that means with that much probability, you are in the 0 state, and 1 minus that probability, you're in the 1 state. Okay, so these alpha and beta, I've been writing mod square, and I hope you know what modulus square is. That means that alpha and beta can be complex numbers, and alpha times alpha star, well, alpha star is the complex conjugate of alpha. That mod alpha square is the probability that I represented here. So alpha can be a complex vector, beta can be a complex vector. They have to follow this rule. And the second important thing that you need to know, so here you can see that R1 and R2 are the magnitudes of alpha and beta. So R1, so I don't need to write mod here because I've already said that R1, R2 are real numbers, but they can be negative, and they're positive real numbers, so you can take their phase out and absorb it into these thetas. Phase as in the signs. So now, what is a restriction on the phase? I can represent alpha and beta that I've written here in the following format. And this factor that I've extracted e to the I theta 1, this is not relevant. only the difference θ2 minus θ1 is relevant. And this is called the global phase of a quantum state, and this is called the local phase of a quantum state. Okay. So we only care about the local phase. We don't care about the global phase. Global phase does not distinguish two quantum states. So for example, e to the I pi 0 and e to the I pi over 2 0, they're the same states. Because here I've only replaced the global state. All right. So why does it not matter for this global phase to differ? There we can discuss how to distinguish two qubits. Two qubits can be distinguished using their inner product or their scalar product, if you know what scalar product and vector products are. So this must be in your vector calculus coursework. So let's take a qubit 1, which is alpha 1 beta 1, qubit 2 alpha 2 beta 2. Okay, so these are represented as follows. Now when I take the inner product of q1 and q2, remember that 0 and 1 cannot, so 0 and 1, the most important thing to know is that 0 and 1 are two orthogonal vectors. That means if you multiply 0 and 1, as in the conjugate of 0, that is a row vector, and the one column vector, you will get 0. That is, they are orthogonal. So if you were to represent it on some graph, you will represent 0 along the horizontal line and 1 along the vertical line, something like that. So 0 and 1 are orthogonal, just like your I and j vector, I, j, k vectors on a 3D graph. Okay. So when I take the inner product, I get the following. I can do the math as follows, and I will remove this one because 1 and 0 will be 0, 0 and 1 will be 0, and you will get mod alpha square 0 0 plus mod. Okay, my bad. So here, essentially, when you do this math, you can show that e to the I theta 1 does not play any role in computing what q1, q2 overlap is, but e to the I theta 1 minus theta 2 will. So this is where you can show that two states which have the same global phase cannot be distinguished. And so it's the local phase only that distinguishes two quantum states. So that's your another degree of freedom. So in one quantum bit, you can choose one of these magnitudes, R1 and R2, so the probability of being in 0 or 1, you can choose that. That's one degree of freedom. And the second degree of freedom is this local phase. That is the sign or the complex number just between these two. Kets. We call these kets, by the way. This is the Dirac notation. So ket 0 and ket 1. This is ket 0, this is ket 1. So I might often use this term, but I would keep on revising that this is just 0 in Dirac notation and 1 Dirac notation. This was just to distinguish the classical bits from the quantum bits. Okay. So fidelity, I think Professor Panigrahi has used this term quite a lot as well. There are different measures of fidelity, and the one I am going to show you is the following, which depends on the overlap. Modulus square of the overlap tells you how close two states are. So if Q1 and Q2 were both 0, that means they were both the same state, this modulus square will be equal to 1. If they were both 1, it will be equal to 1. If 1 was 0 and 1 was 1, then this will be equal to 0. That means this fidelity measure will go from 0 to 1. 0 when they are completely orthogonal to each other. 1 when basically they are the same. But if they are not the same, but also not orthogonal, for example, 0 and 0 plus 1 over root 2. This one will have an overlap of half, because while 0 and 0 will give you 1, 0 and 1 will give you 0, and the square root 2 factor will be mod squared, so you'll get a 1 over 2 there. Okay. Now, if you have two qubits, then you can have four different states represented by two qubits, as you can see. So I'm writing tensor here. It's a tensor product, 0 tensor 0. So the 2 by 1 column vector and the 2 by 1 column vector, when you take the tensor product of those two, you get this 4 by 1 column vector. Then you have 1 1, so you can have 0 0 state, 1 1 state, 1 0, this is 0 1, and this is 1 0, and then 1 1. So these are the column vectors which represent all of these different states. The coefficients in front of these states, again, mod square of that will just tell you the probability of being in this state or this state or this state or this state. So mod b square for this one, mod c square for this one, and mod d square for this one. All right. So this way I've shown you how you can represent various different, you can choose values of A, B, C, D, which satisfy the normalization constraint. And this way you can have any representation, any combination of these 4 different states, any superposition of these 4 different states represented by 2 qubits. And that's basically where these advantages, most of these algorithms draw their advantage. For example, the Grover's algorithm, which you must have heard the name of. Okay, so let's discuss the applications, because these applications decide what should be the, let's say you were not thinking about storing your quantum bits. Let's say to begin with, you just wanted to compute some circuit, right? For that, your qubit just needs to live through that circuit. If it's lived through that qubit circuit and has not had any error, that means your computation is reliable. So I only need to be, if I'm not using my quantum bits for quantum memory, but just for computation, I just need to make my quantum bits so robust that there is no error during these circuits. And that basically depends on how long your circuit is. So we will identify some crucial applications of quantum computation. So the very first one is simulations of many body systems. So the nature is huge, and quantum computers to begin with were Feynman's idea to simulate nature, and nature has nature is a quantum mechanical space, and essentially to simulate nature you need a quantum computer. So the very first use case of quantum computers, when quantum computers were not even there, was identified to be simulations of quantum systems, which includes many body systems. So you will have interactions between different particles and different couplings, or different couplings between these different particles. And to solve those problems, you need current day computers are not good enough. So Bose-Hubbard, to name a few, you have Bose-Hubbard model, lattice gauge theory. These are all different use cases of simulations of many body systems or simulations of nature. Second, of course, algorithms, which you must have heard of. There are some number theoretic problems which are hard to solve, and these have been identified in number theory, basically a subclass of mathematics. One of those was factoring a prime number. You cannot factor a very large prime number, factoring a large number. This is not prime. So it's prime factorization of a large number. So this is essentially the algorithm that Shor's algorithm is. This is essentially what the Shor's algorithm solves. It takes a large number and gives you the prime factorization of it. And such number theoretic problems are actually very important, because some of the problems in nature can use these algorithms to come up with solutions for to solve certain specific problems that we deal with. But primarily these number theory problems are actually used, the hardness of these number theory problems are used in cryptography. We'll come to that in the next bullet point. Then there was a second algorithm, which is basically searching a number, which is Grover's. Love Grover came up with this. This is again using the fact that superpositions essentially can simultaneously search for using superpositions. You can search for a given number in an array, in a length n array, much faster than a quantum computer. Than a classical computer. Okay. Now, like I said, the first one here, prime factorization of a number, that is a number theoretic problem, and it is hard to solve. So people decided, let's use it to our benefit. Let's use the hardness of this problem to securely communicate. over the internet. So they decided that we will give the product of two prime numbers as a key to the user, and I will keep so the sender, for example, will keep one part of this prime factorization, and the user will keep one other part of the prime factorization. When you go to the let's say bank, and the user basically will give this number and the bank will multiply its number. Multiplication is not a hard problem. Prime factorization is. So what's publicly known is this large number, which is a product of these two numbers, but the prime factors are only given to user A and user B, which can be bank and the client, or in any other scenario you can think of other things. Only when the user A and user B meet and present their individual prime factors is when user A can verify that user B is the correct user for whatever account, which represents this large number, and user B can verify user A. So essentially, this is what's the RSA crypto method, and this is the RSA security protocol that we had been currently using. Since Shor showed that factorization of a prime number is possible using quantum computation in reasonable amount of time. I will not quote the order because maybe maybe the complexity notion is not very much known to people. So let's just say that in the life, it's with quantum computers, it is possible to factorize a large number, get the prime factorization of a large number in a reasonable amount of time. So a hacker can actually, to whom this large number is known, can use this algorithm to find the prime factorization and pretend to user A that it is user B, and pretend to user B that it is user A, and that way you are not secure anymore. So so basically after this algorithm, quantum computation people decided that, okay, let's find a solution to this also. And they came up with quantum cryptography. Quantum cryptography actually is interesting because it can give you universal security or information theoretic security, which is not possible in any other setting. So any other crypto protocol which is coming from a classical methods, which is basically using hardness of some protocols, gives you computational security. That means that given there is no computer which can solve this XYZ problem, we are secure. Quantum cryptography protocols actually give you information theoretic security or universal security because you are protected there by the laws of nature. That means you use ideas like no cloning theorem and entanglement. No cloning just says that you cannot clone an unknown state. If a hacker comes in and they haven't, so they can't measure, a hacker can't measure a quantum state, because as soon as you measure a state, it collapses and it loses its quantum information. So if not measured in the right basis. So no cloning plus entanglement between the user and the client and the server, or between user A and user B. Essentially, these two components played a huge role in providing information theoretic security. So information theoretic security just means that there is no computer in the world that can be ever made which can break these protocols. And such a protocol can only be generated by a quantum computer. Let's say there is a computer which is even more powerful than a quantum computer. That is possible. But if it is based on classical methods, it cannot give you such security. So I find this use case of a quantum computer so powerful. It teaches you that nature can actually protect you. Nature can protect your information. And I think this is the epitome of secure communication. For example, recently, so this actually happened 2-3 days ago. People had come up with protocols which are secure against a quantum computer. So there are these lattice-based problems which cannot be even solved by a quantum computer. That is what people believed. And this is called an LWE assumption, or learning with errors assumption. Under this assumption, cannot solve the some problems which are basically related to shortest vector, finding a shortest vector on a lattice or something. And this assumption was enough to actually claim that now these protocols that we design, if you take LWE assumption, they're secure against a quantum computer. 2-3 days ago, there was a paper that came out which claims to solve LWE in polynomial time also. That means that research, I mean, if this paper is correct, so it has to be peer reviewed and checked by multiple people. But if this paper is correct, it just shows you that you can never claim that a protocol is truly secure against a quantum computer or against the next technology, unless and until it's based, it's information, it gives you information theoretic security, it gives you universal security. So this is an amazing example of application of quantum computers. All right. So now let's jump onto quantum errors and really talk about quantum error correction. So yesterday I told you about classical errors, how to encode your classical bits, then how to decode. What does the decoding procedure entail? What are the figures of merit? So just to remind you, it was you want a good code rate so that you have efficiency. You want a code rate, your code rate should be constant. That means, but with increasing protection, you should get the same number of logical bits by increasing the number of physical bits. You should be getting increasing number of logical bits also, and that means this error correcting code will be efficient. Number one, number two, it should have a very easy decoding property. That means it should be very easy to take the quantum information given by my quantum error correcting code or encoding and decode it using a classical algorithm like minimum weight perfect matching, which I told you about yesterday, and tell me which error had occurred. Okay, so this is the second one. The third one is how do you place it on a 2D or planar chip, a quantum chip? That is very important. If it's something like a nearest neighbor coupling, that was, for example, the repetition code, it seems like a more plausible task to do. But if it's something like the LDPC codes, which are used to get you from 3G to 5G speed now in classical communication, it might be harder. And we have versions of quantum LDPC codes. We have versions of the quantum analog of the repetition code, which I will discuss now. And both of these options have their demerits and merits. Okay, so while we have reviewed all the quantum properties and quantum gates, quantum qubits, let's discuss the errors. So quantum errors are as follows. I told you this is a quantum state. One error that can happen is a bit flip. That means 0 goes to 1 and 1 goes to 0. So an unknown state which looks like this will become this now. Another error that can happen is a state with a local phase. So like I said that beta can be some R2 e to the I theta and alpha can be some R1 e to the I theta. If this state undergoes a phase flip, so the sign here or the plus e to the I theta 2, theta 1, theta 2 minus theta 1, the local phase here, if it changes by a sign, that is by a phase of pi, because e to the I pi is minus 1, then you have a phase flip. What you can also have is a phase flip plus bit flip. Now, that means your 0 went to 1, 1 went to 0, and the local phase changed its sign from plus to minus or minus to plus. It looks like this is, these are two errors, phase and bit, phase flip plus bit flip. So they should occur with probability of this multiplied by probability of this. For example, phase flip is, bit flips are Pauli X errors. So Pauli X basically changes 0 to 1. And phase flip basically takes 0 to 0 and 1 to minus 1. While the global phase I told you does not matter, but if it's in a superposition, 0 will remain 0, 1 will go to minus 1, and thus you have a phase flip. So phase flip is the Pauli Z error, and bit flip is the Pauli X error. Pauli XYZ matrices are basically the lowest hierarchy of gates for a quantum for a quantum bit. And these are just 2 by 2 matrices. So let's say the Pauli X error occurs with probability Px and the Pauli Z error occurs with probability Pz. It looks like the phase plus bit flip error, which is Pauli Y, by the way, because Y is equal to iota times Zx, Z as in Pauli Z, X as in Pauli X. If you multiply matrix Z with matrix X and multiply that product with a factor of iota that you see in the complex numbers, then you will get the Pauli Y. And so it looks like Pauli Y error really should occur only when Z and X both errors have occurred. So it should occur with a probability of Px and Pz, Px times Pz. But that is not always the case actually. So the true error that occurs gives you 2 types, can be approximated to 2 types of error channels. One where Px, Py, Pz are all independent. So Py can actually be greater than Px times Pz. Or another one when Px and Py and Pz are all equal. The first one is called Pauli error channel. That is, all of them have their own probabilities of errors. And the second one is called depolarizing error channel, where each 3 of these are equal to each other. And these are the 2 approximations that we can get for the errors that actually occur. The errors that actually occur are decoherence and dephasing, like someone asked yesterday. Look, decoherence essentially decoheres your errors and such. So there's decay and dephasing actually. We can talk about decoherence separately. Decoherence essentially mixes your state completely into a classical mixture, but the primary errors are decay and dephasing. Decay takes all the 1 states to 0 states and 0 states also to 0 states, but it can be approximated as a Pauli error channel. And dephasing just changes the local phase of your qubits. So this phase can be changed not just from plus to minus, but from plus to any plus e times I to the theta. But all of these errors can be approximated to these simple errors, Pauli X, Y, Z type errors. And that's fortunate because it's easier then to actually analyze these errors theoretically or and devise decoders for it, which we can test and simulate. Okay, so to give you a state-of-the-art example, I have plotted some these error rates or lifetimes for qubits, for superconducting qubits especially, because until recently, superconducting circuits were actually quite the most favorable platform for quantum computation. Now I would say it could be superconducting circuits or Rydberg atoms. For Rydberg atoms, qubit lifetime is not a notion. The atoms live much longer than superconducting circuits. There is no notion of qubit lifetime being small for atoms, but their gate times are really long. So your circuit will be so time consuming that it might not be the most favorable thing to do. But also there you can have as many number of atoms, and the lifetimes of atoms are really good. So the concept of qubit lifetimes doesn't come into Rydberg atoms, it comes into superconducting circuits. Why do I care about superconducting circuits if Rydberg atoms are so good? Well, Rydberg atoms are good because of lifetimes and numbers, but gates are slow. Superconducting gates are extremely fast. The single qubit superconducting gates are of the order of nanoseconds. So that's as fast as any any quantum computing platform can go to the state. So the forte of superconducting, one of the forte of superconducting circuits is that you can do really fast gates. So the circuit will be extremely fast. Okay, so this is basically showing you how from beginning to all the way up to now, up until now, the qubit lifetimes. So error rates are basically 1 over lifetimes, and that's why I'm quoting lifetimes here. Like I said earlier, I would like the lifetimes to be the age of the universe. Let's call that 10 to the power 20 nanoseconds. And I would at least want this to go all the way up to 10 to the power 20. However, you can see that the qubit lifetime stuck at 10 to the power 6. So we definitely need error correction on top of it, which can correct for these errors. If this was already at 10 to the power 20 or something, I wouldn't need error correction, at least in computation. But because it's not, I will need error correction on top of these different lifetimes. So these are showing you just these different lifetime curves that have been realized over the years, and we are kind of plateauing now. As you can see, we started from a good 10 to the 0 and went all the way to 10 to the somewhere around 10 to the 5, which is a great fiat, but then we are kind of plateauing now, and it's the experimentalists feel like it's harder, and it's getting harder and harder to just improve the lifetime of the qubits or improve the error rates of the qubits. So now the question is, can we do error correction with quantum? And the answer is yes, and the problem was essentially solved by Peter Shor. Error correction in quantum entails two tasks. One, you can't learn the state, so it's going to be hard to compare whether two bits are the same or not, like we were doing in repetition code. And the second thing is that we need to correct errors in two directions. We need to correct Pauli X errors as well as Pauli Z errors. Like I said, even though Pauli Y occurs independently, if you can correct for Pauli X and Pauli Z errors, then you can correct for Pauli Y also, because Pauli Y is just a product of Pauli X and Pauli Z. So you need to be able to correct for these two types of errors in contrast to just correcting one type of error in the case of classical computation. And we need to do this without having learned the state of these qubits, because that would collapse the state and you will lose all quantum information. So that's not the point of error correction. Error correction's point is that you leave the qubit state as is while correcting errors. Okay, so Peter Shor basically came up with the quantum repetition code, and an easy way to present these error correction codes is the stabilizer formalism, which uses group theory, but you can basically understand this very easily. The idea is that using entanglement and with a third ancillary system, I can, without looking at the quantum state, tell you whether two bits are the same or not. And we went through this yesterday. I said this is a control Z gate between the first qubit and the ancillary system, and this is a control Z gate between the second qubit and the ancillary system. Such type of gates you won't find in classical computation, because you can see that this is some sort of thing happening between two qubits. Like, for example, in your classical case, you have AND gates, etc., which basically operate on two qubits, but this is not like that. This is a very quantum specific gate. It's called control Z in the sense that depending on which state A is in, you will do something to the ancillary system, which is in the plus state. The plus state is this 0 plus 1 over square root 2 state. That means the column vector is 1 over root 2, 1 over root 2. And you basically get this by applying this Hadamard gate on 0. Hadamard is a basis changing gate. So we say that there is one basis, which is the Pauli Z basis, 0 and 1, because Pauli Z the eigenstates of Pauli Z matrix are 0 and 1, and there is the eigenstates of Pauli X matrices, X matrix are plus and minus states, which are superpositions of 0 and 1. So plus is 0 plus 1 over root 2, and minus is 0 minus 1 over root 2. And you can get plus state by applying a Hadamard on 0, and you can go reverse also. If you apply Hadamard on plus, you get 0 state. This is because Hadamard square is equal to identity, actually. And if you apply Hadamard on 1, you will get the minus state, which is 0 minus 1 over root 2. Okay. So what this gate does is, if A was in 0, then you will apply a Z gate on plus on this ancillary system. Sorry, then you will not apply anything on this ancillary system. And if A was in 1, then you will apply Z. So then similarly, if B was in 1, then you will apply a Z gate on the ancillary system. If B was in 0, you will apply nothing. So for example, if AB were 0, 0, because they are 0, 0, I will not do anything to the ancillary system. So the ancillary system stays in the plus state. If AB were in 0, 1, the first gate would do nothing because A is in 0. The second gate, because B is in 1, will apply a Z on plus. A single Z on plus will take plus to minus, because remember, Z on 1 is minus 1. So if I apply Z on this state, Z on 0 is 0, Z on 1 is minus 1. So you get 0 minus 1 over root 2, and that is the minus state. Okay. I think I've written, so this should be Z plus equals minus and Z minus equals plus. I'm sorry about that. Because Z plus and minus are not the eigenstates of Z, so they should actually transform. Okay, now 1, 0 on plus will give you 1, 0 minus, because now the first gate has applied a Z on the ancillary system and the second one hasn't. So you have applied Z once on the plus state and you get 1, 0 minus. And that means now you again have minus in the ancillary system. If you have 1, 1, then both the gates will apply Z on the plus state. But Z square is identity again. You can do this by just, you can check this, but you can just imagine Z on plus will take you to minus and Z on minus takes you to plus. So Z on plus took you to minus, then another Z on minus brought you back to plus. So now you have 1, 1 plus. That means when these two qubits were same, you got your ancillary system in the plus state. And when the two qubits were different, you got your ancillary system in the minus state without harming the quantum information in these qubits. So this is essentially what we can use to do these stabilizer measurements. So for example, stabilizers on these states are Z tensor Z. So I'm basically measuring Z tensor Z. That means measuring Z on these two qubits means doing a control Z from the top qubit to the bottom qubit and from the second qubit to the bottom qubit. I have measured this Z tensor Z using this circuit on these two qubits, and measuring ZZ on 0 will give you +1 because Z is a 0 and 0 are +1 eigenstates of Z. Measuring Z tensor Z on 0 and 1 will give you -1 because Z on 0 is gives you a +1 eigenvalue and Z on 1 has a -1 eigenvalue, as you can see over here. So you will get +1 times -1, -1. So this outcome will give you a -1. This scenario, applying this circuit to this state will give you a -1 outcome, whereas applying the circuit to this state will give you a +1 outcome when you measure the third ancillary system at the end of the circuit. And this way I can show whether A and B are in the eigenstate of Z tensor Z. I'm going to stop calling this Z tensor Z. Let's just call this qubit 1 and qubit 2. So then Z1, Z2, that means Z applied on qubit 1 and Z applied on qubit 2. This operator is a 4x4 matrix. I just want to check whether the initial state of A and B is whether the state of A and B is an eigenstate of this operator or not. And that essentially would tell you the error tracking that we are looking for. We are encoding, where we will say that my 0 logical is 0, 0, my 1 logical is 1, 1, and thus I can figure out that if I'm in the -1 eigenstate, that means I'm in the erroneous spaces of 0, 1 and 1, 0. Whereas if I'm in the +1 eigenstate, then I'm either in 0, 0 and 1, 1. I cannot distinguish between 0, 0 and 1, 1 because I should not be able to, because these are my 0 logical and 1 logical. If I will be able to distinguish between the logical states, that means I am doing something wrong. I am looking at the state. I'm measuring the state. We don't want to do that. Both the code space states, 0 logical and 1 logical, should be indistinguishable under this circuit, and only the error states should be distinguishable. So the stabilizer formalism goes as follows. You use control Z gates to measure Z stabilizers, and you use control X gates to measure X stabilizers. Because X and Z do not commute, measuring these Z stabilizers detects X errors, as you can see here. So 0 to 1 is an X error, I told you in the beginning. And you can see that doing this control Z circuit here, I am actually able to detect this X error, which took 0 to 1 or 1 to 0. Okay. So now I've said that all the Z stabilizers can be grouped into SZ, and all the X stabilizers can be grouped into SX. SZ and SX should commute for all stabilizers. All these stabilizers should commute with all X stabilizers. Even though X and Z do not commute, you can find some combinations of X and Z stabilizers that can commute. And the reason you want to do this is because, like I said, I want to detect both errors X and Z. That means I want to be in an eigenstate in both the bases, X and Z bases. The logical X and the logical, I want to preserve the information about both X and Z errors. And in order to do that, I need to be in an eigenstate of these two operators, because if I'm not in the eigenstate, my code space is, if it's not in the eigenspace of both of these operators, then measuring these operators would change my code space also. So in order for the code space to be a common eigenstate of both these operators, you need these operators to commute, because if they don't commute, they cannot have a common eigenstate. And then we want the errors to anti-commute. That means S times E, where E is some error, S times EI is equal to minus S times EI. Okay. So if you, let's say psi is some state, psi is the actual state, and like I said, the stabilizers, the eigenstates of these stabilizers are my code space. So this code space, when you apply S to it, it will give you just psi. When you apply S on E psi, you can use this identity and put SE as minus S. And now S psi is equal to psi, so this equality follows. And that means so E psi is a minus 1 eigenstate of S. So if you measure S on psi, you should get plus 1. And if you measure S on E psi, you should get minus 1. And that is exactly what was happening earlier when I showed you that 0, 1 and 1, 0 would have taken the ancillary state into to minus, and thus when I would have measured that state, I would have gotten the minus 1 outcome. And if I would have measured it in 0, 0, 0 and 1, 1, I would have gotten the plus 1 outcome. So that was exactly what was happening. I was measuring the stabilizer Z1 and Z2, Z1, Z2, or Z tensor Z, and given I get the outcome plus 1 or minus 1 in the ancilla, I get to know whether I'm in an error state or in the code state. All right. So we reviewed this eigenvalue problem yesterday, so I'm not going to go into it, go into the details of this. I will get down to something interesting. So to summarize, I told you that in quantum error correction, the encoding requires you to understand group theory well enough, because the error correction strategies that we are using involve measuring these stabilizers, and basically all our codes are stabilizer codes, and the stabilizer formalism comes from group theory. And for the decoding part, you need to know graph theory. So if you're interested in these kinds of things, group theory or graph theory, you can employ it to good use for error correction. Now let's discuss an example of an error correction code. This is a very prominent example. This is what Google has been using for a long time now, and they just demonstrated this code and how it works recently in an experiment in 2022. So so these circles that you see here are basically your qubits, and the shaded portions represent x tensor x tensor x. That is, I want to measure x tensor x tensor x tensor x on these 4 qubits in the square. So now I have a 4-body stabilizer. Earlier I was talking about 2-body stabilizers, Z1, Z2, Z tensor Z, that is Z on first qubit and Z on second qubit. Now I want to measure 4-body stabilizers. And then these unshaded boxes are Z tensor, Z tensor, Z tensor. There should be another Z here. So 4-body Z operators. Then you have your 2-body operators, Z tensor Z, Z tensor Z, and X tensor X, X tensor X. Where did this come from? So if you remember, we were discussing repetition code. So this one line is actually a repetition code in Z. You can think of it like that. This another line is another repetition code in Z. This line is a repetition code in Z. And this line is a repetition code in X. This line is a repetition code in X. This line is a repetition code in X. So simultaneously, you are sort of, via this surface code, you are basically looking at a superimposed, 3 superimposed Z repetition codes and 3 superimposed X repetition codes. You can't just take, oh, let's take this as the repetition code, this as X repetition code, and that's it. I just need these 5 qubits to do X and Z error correction. That wouldn't work. The way to compose one error correction code into another error correction code is that you take this entire thing. This is a Z repetition code, sorry, X repetition code, X repetition code, X repetition code, and then you're basically doing a Z repetition code on these 3-qubit XX repetition codes. So think of this whole thing as one entity, this whole thing as one entity, this whole thing as one entity, and then you're doing the Z repetition code on these 3 entities so you can think of it in that sense. And when you do this more formally, you get these stabilizers. And so all these SX will give you your Z, will give you information about your Z errors, and all your SZs will give you information about your X errors. For example, let's say this qubit underwent an error. If this was an X error, the measurement of this stabilizer and this stabilizer will be -1. If it was a Z error, the measurement of this stabilizer and this stabilizer would, sorry, if it was an X error, the measurement of these two stabilizers would be -1 because these are SZ stabilizers. If it was a Z error, the measurement of these two stabilizers would be -1 because Z anti-commutes with X. If it was a Y error, all these 4 stabilizers will be -1. So this way, error correction circuits give you some information about the errors. Okay. All right. So like I said, an X error basically makes an edge like a right diagonal. A Z error will basically give you these two. I'm gonna start whenever I get a -1, I'm gonna say there is a node. Remember, we were basically comparing 2 bits, and if their bits did not match, I would say that there is a node there when I was relating them to a graph. So I've basically put a node when there is an X error, I get the these 2 nodes, which I can connect by a right diagonal edge. When I get a Z error, I can connect the 2 nodes that appear with a left diagonal edge. And if I get a Y error, I get this crossing type thing. This way, I can get a few different graphs for X and Z. So if you can think of all the different errors that can light up, you get graphs like this and similar graph for Z. You can feed this into the MWPM decoding algorithm. And then what it gives you is just one node connected to one other node. And you say all the qubits that pass through that edge have errors. Okay. This surface code actually comes out of a very complicated form of condensed matter theory. These are topological codes which satisfy the BPT bounds. BPT bound is actually the max, it tells you the maximum number of logical qubits you can encode in a number of physical qubits. That is the it tells you the maximum amount of information that can be stored in n physical qubits. So it is a great resource, but this BPT bound was satisfied for this code where you can just think of this surface code, and if you connect this end with this end and this end with this end, it becomes a torus. So think of a donut and place all these stabilizers on a donut. If you cut this donut along one circle, the larger circle, and then cut that, you basically get a cylinder, and now cut this cylinder also along the height, you get this 2D plane. That's how you get the surface code. So originally, Kitaev came up with the topological code, and it had amazing properties, but a donut is not a 2D surface. How will you make a chip on a donut-like surface? So in order to map this onto a 2D chip, people basically did this trick and got the surface code. So that's called the surface code, but it doesn't have the same properties, but it is the best thing we can do with nearest neighbor couplings, which is a very easy thing to realize for superconducting circuits. Rydberg atoms are not really limited by connectivity, etc. All right. So for example, this is a picture I took from the Google experiment. All these different circles that you see are your qubits. So the blue ones are your ancilla qubits to measure stabilizers on these data qubits, which are in yellow. They show this, so they have this entire patch, and they show that, okay, you can use this, they use this patch to do a 3x3 surface code. That means a 3x3 lattice. And then they use this entire patch to do a 5x5. You can see that here you have 5 qubits. And I showed you the example of this 3x3 patch. So technically, if you were below threshold, if you remember what threshold is the probability of errors rate, the probability of errors below which, by increasing the size of your code, you're going to reduce the logical error rate, which is an important property, and we want that property. So they did this experiment on the error correction experiment on 3x3 lattice, and then they did this experiment on a 5x5 lattice, and they got the following graph. So the y-axis is the logical error rate and the x-axis is the physical error rate. And you can see that the blue line, which is d equals 5, has a lower logical error rate, is lower on y-axis compared to the red one, which is d equals 3. So they showed that, in fact, by increasing this whole theory that I've been talking about, that by increasing the number of qubits, they were actually able to reduce the logical error rate. And this is very important for the demonstration of error correction. Now, let me show you the graphs for the surface code experiments so far, actually. If you truly think about error, so that graph sort of showed you that we are below threshold. They are yet not at the break-even point where, so this experiment did not show you how well the single qubit can do. For a single qubit, these logical error rates are very high. The single qubit error rates are lower than this. So technically, the Google surface code is below threshold, but not yet below break even. So now I'm going to show you which experiments have passed break even. That is, your error correction code performs better than an uncorrected qubit, which is a proof of principle demonstration of error correction. So there are these different types of codes that have been implemented over the years. And on the y-axis, what you see is basically the logical and the physical. So on the y-axis, we have plotted time in microseconds, basically. For all these different labels, which are different types of error correction codes, the bottom point shows the physical lifetime, that is the lifetime of an uncorrected qubit quantum system, and the top point shows you the lifetime of a corrected qubit. And you can see that, so Google's error correction experiment is actually this SC2, as you can see here, and SC3. So SC1 and SC2 were actually done by error correction experiments done by academic labs. SC3 is Google's experiment. HH is a heavy hex code, which is IBM's experiment. CAT, BIN, GKP that you see here, these are actually very different types of code. These are oscillator codes. These are rarest of the rare breed, because these are the codes that have only been executed in trapped ions and superconducting circuits. And you can see the best error correction gain is actually for a code called GKP code, which got its name from its founders, Gottesman, Kitaev, and Preskill. This is Daniel Gottesman, who found the stabilizer formalism, Kitaev, who found the topological code, and John Preskill. I am sure many of you know who he is. All right. Okay. So these are, I don't think I will have time to discuss what these oscillator codes are. And this GKP code is essentially my expertise and my current research interest, in fact. So it would be great to talk about this, but maybe some other time. So I've just basically shown you the state-of-the-art experimental results for error correction in terms of threshold and break even. I think I'll stop here and take questions.
Yeah, thank you so much. So, now I'll request the participants to ask the questions if they have any doubt.
I'm sorry I can't be heard. Can you hear me now?
Yes.
Okay. The second half of your talk was somewhat heavy duty for me, but the first part was very understandable. I mean, the first half of today's, I meant. Yesterday's was very clear. What is meant by a topological state may not be clear to many students. So could you clarify that? And what has Kitaev got to do with it? Is it the same as the SYK model that was mentioned by Prashant Panigrahi earlier, yesterday?
Actually, no. So topological codes are basically codes where the entanglement entropy grows linearly with the distance between the qubits, and that's the only requirement for a topological code.
Okay. I see.
And it's been shown that such codes have the best threshold so far.
Okay.
Best threshold in the sense, the higher the threshold, the better it is, because then we can start doing error correction. We can't start doing error correction if we are past the threshold point.
I see. And your own expertise, as you mentioned right in the end, was in this one particular
GKP
part.
codes.
Can you show that slide again? I need to understand
Yes.
that, at least broadly.
Yes, indeed.
There it is. Just the last, this one. This one, what is it? Can you explain it a little bit?
Yes. So these are oscillator codes. We basically, so far I've been showing you that I can take multiple qubits and encode one logical qubit in those multiple qubits. But you can take quantum oscillators, which are multidimensional systems. They are not just two-dimensional systems like qubits. They're multidimensional systems. So I will use the redundancy in those multiple levels and encode my information such that that oscillator represents two states. That way I can use a single system to protect errors. So far I was telling you that you have to use multiple quantum systems to error correct. But this is one strategy where you can use a single system to correct errors.
Okay. All right. Thank you. I'm sure some other people may have questions.
Any question? Oh, that was a good one. So,
is Amrita there? I think. Amrita, do you want to say something? No, either she's muted or something.
she can unmute.
I think only the co-host can unmute, I find always.
No, attendees can unmute now.
Okay, please allow that.
Everyone is allowed. Can unmute.
Okay, maybe they don't have. But I think what they should do is look at your slides, which are quite clear. I mean, the best thing part about you is that it's like a lecture. So it's not a transfer, so that I can always, at least the first 1.5 hours, 1 hour yesterday and half an hour, I think I can zoom through by just looking at it again and remind myself. Okay. So please, if there's any other questions people have, Shraddha is always available for it. Will you be coming to India anytime in the future?
Yes, I think November is when I will be in India.
Okay. So let me know when you're here so that we can try to meet. Okay.
Yes, indeed, sir.
Yes.
Yeah.
So, thank you so much. Thank you to all the participants.
Thank you, sir.
Thank you to our resource person, Shraddha. So the presentations were really good and quite informative. Thank you so much.
Thank you, Shraddha, very much. Thank you, Prashant. Wonderful it was for you to give time. And I hope you have a great Sunday now. They have a whole Sunday. Our Sunday is over, but you have the whole thing. What time is it over there? I'm curious. It's 7 o'clock here almost.
Yeah, it's 9:22 a.m.
Okay. Thank you, Amrendraji, and thank you, Himanshu.
Thank you. So we'll be connecting tomorrow again.
Yes.
And
okay, bye, Shraddha.
Just one word for the other participants. I think the teachers are there.
Kya hua?
So just wish to clarify this. No, it's not a CBSE training, so no certificate is being supposed from this side this time.
Right.
So thank you all. We'll connect for the last session tomorrow. The same.
What time is it tomorrow?
5:30.
Okay. Thank you.
Thank you.
Bye, Shraddha.
Bye.
Hi, sir. Hi, everyone. Thank you.